So, yeah, we're going to talk about nuclear or decay data. I'm going to take out the nuclear because there's going to actually a broader term for alpha emitters, but actually this is for all radionuclides and it covers quite a very broad area theme field. So we'll start with some really basic nuclear physics or decay physics, and we'll just go through there so I can just cover quite a lot of what this all is about. So radioactive decay, we all know, is a stochastic process by which the unstable atomic nucleus undergoes a spontaneous transformation. So we can do this through the alpha decay, beta decay, gamma decay, positron emission, or electron capture. There's a lot of different routes, and this is all just to get rid of the excess binding energy of these unstable nuclei. And this excess energy depends on the difference in the mass of the parent atom to the daughter atom, plus the particle emission. So alpha emission, you get some extra things to do with conservation of momentum because they're big particles and they go different ways. So each of these radionuclides undergoes its own unique process to lose its excess binding energy. So for example, so this can be achieved through multiple pathways. So as Dennis alluded to earlier, we can have a beta decay. So this is lead-212. I know we're talking about alpha particles, but everybody's considering lead-212 as an alpha therapy. But even though it's actually the progeny that emit the alpha. So when we're doing this, it can decay to the ground state about 13% of the time. So you'll end up with no gamma emissions. But if it goes to one of the higher excited states of bismuth-212, then you'll get some gamma emissions following through it. So a decay of a single atom will only go through one of these paths. And this is illustrated by this decay scheme that we're seeing over on the side, on the right-hand side. But some of these radionuclides can decay by more than one type of decay process. So for astatine-211, it can either decay by alpha decay to bismuth-207, or it can decide to go through polonium-211, or decay by electron capture to polonium-211. And these can have different decay branch probabilities, and these are again things that we need to measure and understand. And then we have, sorry, I already said it has a broad term. So these are values that define the decay process, or the values and arrangement associated with the decay process of the radionuclide. And it covers multiple parameters such as the decay scheme, the energy of the excited states, spin states, though possibly many people don't use this for in normal practice, emission probabilities, which people definitely do use in practice a lot, and half-lives. And these have to be determined experimentally, and they're all measurable quantities. Then we come on to atomic decay data. So this can also be, this decay data term also covers this. And this is the data associated with radiations occurring from rearrangements of the atomic electrons, such as X-ray emissions being Auger electron emissions and internal conversion electrons. And these also have associated energies and emission probabilities, again, which are measurable quantities. So then we come to radioactive decay constants. Most people just know this as half-lives. So these are critical. We need to know these. This is all about, we talk about comparing standards, knowing activity. So if you don't know your half-life and your half-life isn't constant, or radioactive decay isn't constant, we wouldn't be able to compare measurements of the same solution at any time or space. And that's kind of critical for the whole traceability process for activity. But it's impossible to predict when a single atom decay, but we can do it when we have lots of atoms. And the number we get is when we have half the quantity. The half-life is when we have half the quantity, or the time period to get half the quantity of decays. And we know the half-lives have a huge range of very, very almost instant to longer than the universe for half-lives. So we'll go back to emission probabilities or intensities, depending on what people prefer at this moment in time. There's always this discussion about are we using probabilities or intensities? So you could almost say they're the same thing. People will disagree. We'll see how that goes. So along with the half-life, these are probably the most important values for everyday use. These are what's emitted, the probability of these being emitted, and we can use these to work out the activity of a product or a radionuclide that we're measuring. Or that's in a patient and decaying, so we can model that information out, and that tells you more about the dose. So these are the probabilities of any given emission arising from a single atom decaying, but you can also do it as per 100 disintegrations. But as a stochastic process, it's like flipping a coin. So we could flip a coin 6 times, we could get 6 heads. The probability is very small, but when we're measuring radioactive material, we're not just measuring one atom decaying, we're measuring lots of decays. So at which point these numbers, these emission intensities, probabilities, they're almost become, well, we can almost think of them as a constant value when we're having such a large number of decays. And then we come on to decay chains. So Dennis has gone through this a lot and talked about BIPM equations and how we solve them. And this is where we need to know the half-lives very accurately, or we need to know them well. And we need to know these branching ratios as well, because that will define this ingrowth curve, decay curve. We can also think of cross-section data, or reaction cross-section data, as a type of decay data. So obviously we know that radionuclides can be produced from stable or unstable isotopes by firing different particles at a target. And there are different reactions that we can use to create the same radionuclide. So there's a list for, we can fire lots of protons, deuterons, or gamma rays at radium-226, and we can eventually result in actinium-225. Or we can go through spallation of thorium-222 and produce radium-225, or you can produce actinium-225 directly. Somebody just circled it. So, the nuclear cross-section, so the nuclear cross-section of the nucleus is the probability that the nuclear reaction will occur. And these can be different at different particle energies. But these are, again, measurable. We need to look at these. We need to know these for understanding the production yields for when we're producing radionuclides, especially for medical usage. So why have I just gone through some really, really basic radiation physics or nuclear physics? It's essentially all of this nuclear decay data are measurable quantities, and they all have some impact within nuclear medicine at some point in the clinical radiopharmacy pathway. So we have production and supply, all the way through the preparation of the radiopharmaceutical, administration, quantitative imaging, and then dosimetry. So there's some examples at the bottom of the slide where we have where the cross sections go into production. Obviously, half-life is very important for activity. Also, we need to know for dosimetry if we're having the decay branching ratios. And then we have things like gamma ray emission intensities, which are useful for quantitative imaging to get activities for what's in an organ or a region. And for quality control, you need it for knowing that you're going to be releasing a clean or the right activity or the right clean product. So, for example, if we don't know our gamma ray emission intensities very well, we can end up misidentifying or not identifying contaminants. So this, I've actually seen this occur with some really poor data. And yeah, once you fix the data, it kind of resolves itself, and there was no contaminant at the end of the day. But we can also, and that's the same with the half-life. If we're talking about decaying sources, you can, if you've got the wrong half-life, you can then suddenly think there's something else there or not there. It's just the way it is. And then we can talk about how does metrology underpin decay data. So Dennis has given a very excellent talk about metrology and traceability and how this is useful for activities. And he also showed that you can turn it around. So if you know the activity of something, you can work out the decay data or emission intensity. So as I said a lot previously, decay data parameters are measurable quantities. If you've got something that's measurable, you should probably have standards and traceability that underpin measuring these quantities, because we can all take them. So we need to have the confidence in the data that we're using. And that comes from this traceability and these standards. And we can also have primary standards on the, also have added benefits for determining these absolute emission intensities. So without knowing the absolute activity for a primary standard, for example, when you're doing emission intensities, especially for gamma ray emission intensities, there's also other competing processes of internal conversion. And unless we've also measured those values as well, so they can be theoretically determined. But if you don't know your absolute activity, you have to take those into account, and you'd have to do those calculations, at which point it drives some uncertainty into the process, and it's kind of frowned upon at that point to start going through that process. So at that point, you're only providing normalized emission intensities. But with the primary standard and absolute standard, we can skip knowing our conversion electron coefficients or internal conversion coefficients, and we can move on straight to this is the absolute emission intensity. And you can see that it's traceable. There's traceability chain on the side. Mouse. Yeah, there we go. So we can have your primary standard, you get your secondary standard coming from an ion chamber or some equivalent. And then we use those standards to, say, calibrate our germanium detector to get an efficiency curve. And if that can be used then to give you a gamma ray emission intensity. So if you didn't have a primary standard, be normalized ones. So normalized is when you're kind of you're using you're normalizing everything to the major gamma emission. But if you do have that primary standard, we can then get those absolute gamma ray emission intensities out. So I'm going to give some examples of recent decay data measurements. So with radium-223 and decay progeny, gamma ray emission intensities. So we know that we got radium-223 and decays through a whole series. And we know that most of the time we're going to be measuring this in equilibrium. So we're going to look at all the decay progeny in equilibrium as well. So when we're trying to work out the activity, maybe we can use all the emissions coming from that radionuclide or the whole decay series, sorry. So radium-223 is quite complicated on its own. It has a lot of alpha decay pathways, followed by a long, gone now. So it's about 100 or odd gamma rays coming in the whole decay scheme. But there's a total of 148 gamma rays from the entire decay series. One of the things when we started looking at this is that there has been no previous absolute gamma ray emission measurements, just normalized values are available. But we can calculate those absolute emission intensities from the decay scheme itself. So you can balance the decay scheme, and it can end up giving you outputting a scaling factor or a correction for the normalized values. But in this previous work, or the work we did to do the standardization at MPL of radium-223, we can see that the gamma ray spectrometry value down at the bottom is in really good agreement with our primary standard. So there's no problem. Why do we care? We can move on. The nuclear data around. That's just kind of a trick of the data, because when I did the activity for this from the gamma spec, I just took the weighted mean of all the values, and that just ended up luckily ending up where the primary standard value was, or more or less. But in reality, there's an 18% range in the activities just from these main gamma ray emissions. So it's quite and you can see that's in the same radionuclide itself. So even at the low energy ones for the radium-223, they're very high, and then we've got these low ones. What turns out is there was some poor nuclear. One of the major papers that went into it, or one of the data sets, they had used nuclear decay data for a particular radionuclide that was really poor to calibrate their detector. And then when they went to calibrate to do those emission intensities for radium-223, that really poor data transferred onto the radium-223 to produce really poor data. So if you're using poor data, you're going to get poor data back out again. So one of the problems with this is if you're looking at that as a data set, and then you're seeing differences to other techniques, for example, why would you trust this data? It's rubbish, what you might say. It's large spread. There's not a lot. You can't have a lot of confidence in it. And yeah, so if you don't have that confidence in the data, this nuclear decay data you've got here, well, how can you have the confidence in the activity that's coming out or what you're using? And yes, as Dennis used this slide, I had a bit of a sigh when he did this. But one of the things, yeah, so one of the things is while we've done this at MPL, there's already been done at NIST. We've done it. There's been done. These measurements have been done at PTB. There was a comparison or a larger exercise in the Maruli et al. I think that had 3 laboratories or NMIs involved in that one. And there was a later one in 2021. And if we can look at this data and we can go, well, there are really big differences, as Dennis mentioned, to the previous evaluation in DDEP. And it's all been measured by NMIs, but there is one problem. It's not a massive problem, but there is still this inconsistency in the data set just across NMIs. So this is using the absolute emission intensities. We can look at the reduced chi-squared. We'd hope it would be 1. And some of them are not 1. They're much higher than 1. But actually, we move on to relative emission intensities from the same data sets. And those reduced chi-squared values just drop down to almost 1 in some places. And other places, they're still just as poor as they were before, or not as good. The agreement wasn't there. But that kind of gives the impression that while from the previous data, from the previous table, that it may be just the primary standard, or the standard they're using, or we've been using, aren't equivalent quite yet, or there's been some problem. But there's equivalency within our gamma ray emission intensity, which will normalize values that we're working with. But this is resolvable later on during evaluations, because then the evaluator can choose what they consider to be the best data set, or see how it compares against the calculations or theoretical values. But we can see from the radium-223, there's been a new evaluation in 2021 compared against what's happened in 2011. That's taken all these values into account. And what it shows is there's been a really big improvement in the precision of the values. And there's been what we say is an improvement. We can't really say it's an improvement, but there's been big changes made to what the absolute emission intensities actually are. So we can move on to thorium-227 as another example. So this is incredibly complicated. There's about like 240 gamma emissions coming from thorium-227 decay alone. There's a lot of alpha decay pathways. But the problem is it's like the absolute emission intensity itself has been calculated from the decay scheme, and the decay scheme itself is actually not particularly well known. I'll come back to that a bit later. So there's about an 8% uncertainty on any activity you calculate with the gamma emission intensities, because it's a correlated. So because it comes from the decay, calculate from the decay scheme, that uncertainty is correlated across every single gamma ray. You can't erase it. It has to be 8%. There's a minimum you could have. And this is because all the previous data has been published either in the 1960s or from a private communication in 1992. Why we're using a private communication, I don't know, but it was like there was some data that the evaluator definitely wanted to use in it. So this work's been done at for thorium-327 primary standard, and emission intensity has been done at MPL. And hopefully NIST will publish theirs soon. And Dennis hasn't mentioned that these numbers are all wrong, so fingers crossed everything's okay. When's that coming out? Okay, fair enough. So here we see again that there's quite a large scatter. There's a large scatter in the numbers, the activities again. So these are about 11% spread. There's a negative bias of about 3.5% if you took the weighted mean of all these values. But one of the biggest problems is the red line in the plot that's the primary standard value, and the uncertainty is a dashed line, but you can barely see the dashed line. So it kind of comes across the uncertainties themselves, and the thorium-227 emissions are just really big. But if we have a look at the comparison between previous work, because the uncertainties on previous work, the previous literature values are very large, the reduced chi-square is actually okay, and we have agreement. But the MPL values are about an order of magnitude improvement in the precision. So it's always useful to have additional data sets of equivalent precision, so we can compare and show that these numbers are okay. Because if I'm just comparing against something with a very large uncertainty, you can't. What is the comparison there? It could be anything. But these numbers, the gamma emission values feed into the time zero determination. So just to recap, that's the time when there's only 100% of the activity in the solution is thorium-227, and we have no decay progeny at this time. And why we care about time zero determination? So for thorium-227 itself, we do a chemical separation because it's never going to be in equilibrium. And if we're trying to work out the activity or possibly stick it in a patient, you'll want to have those decay progeny gone, and you'll need to remove them. So we can find out a fixed point in time where we are for then working out what the ingrowth corrections are. We can also work out these ingrowth or the time zero with gamma ray spectrometry. So you can just work out the activity of a decay progeny and your parent, and you can look at the ratio, and that'll tell you where you are since you had no decay progeny. But if we're looking, we're trying to do this with the older data. So this is pre-2015. So this is pre-radium-223 new nuclear data or gamma emission intensities, and the same for thorium-227. You can see there is a bias. It tracks down with time, and the uncertainties are again massive. So we're seeing like large 18% relative efficiency, or sorry, relative uncertainties of the deviation. So there's not a lot of confidence in that, and then you might think your chemical separation is okay. So this is all. Having this determination is also something that's quite useful for seeing if your chemical separation is good, because we've done this at MPL where we had somebody use the wrong resin, and as a quality, we always do the time zero calculations on thorium-227, and so you see the output was that we're half a day away from the separation time. So if you just took the separation time, you can end up with very large errors if something goes wrong in your process, and it's a really good check. So, and if you've done it works well, as we've done it at MPL many times now, we can find that our chemical separation and the measured time zero agree within minutes. So, so it's a good quality check, and we can use the updated nuclear data from what's happened since 2015, from the different NMIs and from the thorium data and the MPL, that actually we suddenly get a deviation from the midpoint or the chemical separation time that's much more tightly known. It's got much lower uncertainties, and as we have more confidence in the numbers coming out for working out what this time zero calculation, and that feeds into everything that comes after. So I'm going to do this one as a final one because I only had 30 minutes and I think I might be about to overrun. So actinium-225 half-life. So previously everybody's been using a half-life of 10 days, and this is from a single measurement in 1950. This is kind of a lot of the story about a lot of the nuclear data for a lot of these non-conventional radionuclides, that they've mostly come from nuclear physics experiments or old measurements done some point in distant past. And now the interest in these radionuclides has been revived. So we're now looking at the data again and finding these large differences. But for actinium-225, there was a very nice piece of work led by Stefan Pomme at JRT Gale, along with a very large collaboration of people who used 6 different methods to look at the half-life of this, and they got a much more precise value. It agreed with the current value of 10 days, but that's got a 1% uncertainty on it, and that propagates very quickly into your activity that you're actually calculating. But since then, there's been a large number of, so this is taken from a new evaluation by the DDEP. So this is there's been a large number of, or a significant number of measurements since then from other established different NMIs that have come out. And we can see they all have very good precision in comparison to the old value. But they are about state-of-the-art measurements, about 0.1, 0.2% uncertainties on these, or less than 0.1% uncertainty, sorry. Now that's kind of where we are a little bit with the state-of-the-art for half-life measurements. So the status in these are radionuclides being investigated right now. There's really good review by Alan Nichols. He's gone through a lot of pretty much all the radionuclides, all the different methods, all the different modalities. So he's looked at all of them and got recommendations, and he's got recommendations for atomic data, so LOJA, electrons and things like that. There's another one that's come out as a deliverable from PRISMAP. So this mainly focuses on nuclear decay data for day one radionuclides, but it has some that aren't in the Alan Nichols review, and it has some extra recommendations. So you can find those at these different links. So if you're interested in measuring any, or we want to see what the current state of the radionuclide, your favorite radionuclide right now is, maybe go and have a read. But some of the outputs from that so far, so we have terbium-149, obviously not used a lot right now, mainly due to how difficult it is to make, but also it's 4-hour half-life. But it's the half-life data needs a lot of work. The alpha decay branching ratio, so it decays by alpha or positron or electron capture routes. But the alpha decay branching ratio uncertainty on it is really poor. It's really imprecise. So new studies need to be looked at for that. So that's something we're actually going to do right now. We can talk about more gamma ray emission intensities for pretty much everything. For acetine, it looks good. We just need extra new half-life determinations would be nice. Actinium-225, it looks... So there's been a lot of work on actinium-225, but I haven't seen new absolute gamma ray emission intensities coming out in the paperwork or the publications yet. I'm sure they are coming, but those are things that are also needed right now. And thorium-227, yeah, so NPL's done some work to improve the data on that, but NIST will hopefully produce something soon. But there's also more knowledge. So the decay scheme that needs looking at again and tidying up, because there's a lot of unplaced gamma rays and possibly misplaced gamma rays in that decay scheme. And because you can use, once you know your decay scheme well, you can calculate out a lot of extra the details for, like, say, for the alpha emission intensities and things like that. So moving from that, so one of the other things that's really important for decay data is their evaluations. So we can go around, we can measure all the data we want, we can publish everything, we can enjoy ourselves doing all this and technical stuff. But at the end of the day, all these data sets need to be brought together for a particular radionuclide to be turned into something that gives us a more comprehensive values. So we can all measure something, but if there's 6 different papers on gamma emission intensities, which one would you use? And are there outliers? What's the quality of the data? And this is what these evaluations do. And they basically bring everything together. And somebody like Brian will spend months, years, looking through the data and coming up with, trying to evaluate it to see what is the best data set and what's the most comprehensive set of numbers. And without this, these are the numbers that you are pretty much always going to be using. But without these evaluations, that wouldn't, with all the evaluators specifically, that we wouldn't have these data sets. And we might all be using different data instead of being able to just draw from a single database and then all use the same number. It's always useful to see everybody using the same number rather than everybody using different things. But due to there is a bit of there's not enough evaluators, put it that way. So there can be a significant lag between the publication of new data and its inclusion in new evaluated data sets. And yeah, there's too many radionuclides. We're all looking at lots of radionuclides. We're all wanting to use lots of radionuclides right now, and there's just not enough evaluators. And part of that might be because there's not enough recognition from funding bodies and things like that for doing this sort of work, and how critical it is to everything we're doing and where it comes in. So that comes into current challenges, and recognition is one of them. undeniable between funding and recognition, but I thought recognition is more important because if you're recognized as important, you're more likely to get funding. So as we talk about evaluators, they need to be recognized. That sort of area needs to be recognized as important, and more effort and more funding going towards that. But that's also the same for the measurements of the nuclear data. So for my sins, I've been working NPL for 25 years. But it's only over the last 10 years that nuclear decay data measurements where I am and what I've seen has really kicked off at a high intensity. Before that, it was sort of gone, that'd be nice, we'll hide it away, we'll do it somewhere on our Friday afternoons, and then we might publish something. But now we're actually seeing there's a lot more interest in this. And that's only a good thing, and that gives us more possibilities to really get on top of the decay data and really improve it. We also have technical challenges. So some of these numbers or measurable quantities are difficult. Some of the radionuclides are difficult. It comes from things like the primary standard themselves can be tricky. Thorium-227 being one of them, and I agree, it was the most fun. And then we have skilled people. Again, we need the right type. We need those people coming in who've been trained, who are enthused by this, to come in and carry on this work. And finally, we have the robustness and validity of the data we have. So this is something that keeps coming up, that we need to have the confidence in the data we're using. It doesn't, and we need to find ways of making sure that that data is robust and it's valid, and that can come through the traceability and metrology that we use every day for activity, we can use for generating our nuclear decay data or decay data. So future outlook, well, I think it's really good at the moment. So there's lots of new programs coming out. So we have PRISMA, we have Alpha-emitters. The Department, UK government has got the Medical Radionuclide Innovation Program. And these have got built-in metrology to measure decay data for the medical radionuclides. This is excellent. I'm sure that there are lots of other programs that I don't know about, but those are the ones I could think of at short notice. And then we have NUPEC. So this is the nuclear physics community for Europe. So they're having their long-range plan, which is currently in progress. And there has been an identification of decay data metrology and the needs for that within societal applications. So there, final slide. So in conclusion, decay data is a broad term covering a large field. Decay data are measurable quantities, and a lot of the data currently is old and does not benefit from traceability or metrology. So we need to do more to improve this data and go back and having a look at it. Nuclear decay or decay data has an impact across the whole radiopharmaceutical pathway. And over the last at least 10 years, there's been significant improvements in the data that's been coming out. Been using state-of-the-art techniques with metrology and traceability inbuilt into it and robust uncertainties, especially within half-lives. And decay data is seeing an increase in interest and the need for better confidence in the data. And it's great, Grant. I think the future bright for this. So there's new programs underway that identify the need for metrology and decay data. Okay, thank you very much.